Hello all and welcome back to our lectures. Today we'll be talking about functional groups and alkanes. Alkanes will be the first class of organic compounds that we're going to start with. Before we do that, as usual, I have a beautiful quote for you. It says, "There are no secrets to success. It is the result of preparation, hard work, and learning from failure. Even when you fail, it becomes an education for you. It becomes a stepping stone for you to keep moving on, to keep achieving success." This quote is from Colin Powell. Colin Powell was a retired 4-star general that served as a national security advisor, and later he was the 65th Secretary of State. He served under the Bush administration. In fact, he was the first African American to be appointed as a Secretary of State in the United States. Okay, so this is all about this. Then let's take it off immediately. Now, what are we going to achieve in this class? At the end of this lecture, we're going to be achieving these goals. Number one, we're going to look at the functional groups and their significance. What is their significance? Why do we even have to talk about them in the first place? Now, we recognize and classify organic compounds using their functional groups. And then we'll now understand and recognize different conformations of alkanes and draw their structural formulas. We usually think that alkanes do not have functional group because they are just made up of just carbon to carbon single bond. They are just saturated hydrocarbons. But we're going to answer all these questions by the time we start this lecture. What are functional groups? Let's start from there. Now, functional groups are groups of atoms or bonds. It could be atom, it could be an atom, it could be a bond. It could be groups of atoms or bonds that differentiate molecules of organic compound from one class to the other. They are the true identities of this class of compound. So if we see an alcohol, we know it has an OH as its functional group. If we see an organic acid, a carboxylic acid, we know it has COH as functional group. So they are actually what identifies this class of organic compound. And not just that they do that, they also determine both their physical and what chemical properties. You know, these particular bonds will tell us whether is this a polar bond or not. If it's a polar bond, there's the probability that it's going to be soluble in water. And then there's the probability that it's going to have higher boiling and melting point. These are all the information we get when we recognize the particular functional class or functional group in that particular class of organic compound. So except for the alkanes, each functional group contains at least, a functional group must contain at least a multiple bond or oxygen or nitrogen atom, apart from alkanes. In fact, at times, some of my students, when I give them some questions at times to identify a functional group, and they give me, I have something like this, and they tell me this is an alkane, I usually grade it. So alkanes are known by having carbon-to-carbon single bonds that are completely saturated. That is okay. But in the true sense, the alkanes do not have any functional group. But every other class of compound can be identified either by their bond or by the atoms attached to them that actually identifies that class of compound. Now, I have some examples of some of them here. Now, this functional group is for alcohols. This is for the alcohols. Of course, alcohols have the OH group. The OH group is a very polar group. Like I said, most alcohols are soluble in water because of this polar group. Now this is the carboxylic acid. The carboxylic acid is characterized by having the carbonyl carbon and the carbonyl group. That's the carbon with double bond oxygen. And on this carbonyl carbon, it has another OH. So it has both the OH of this one and a carbonyl carbon. So this class is what? The carboxylic acid. Carboxylic acid. That's what we call them. We call them the carboxylic acid. Okay, let me try to make that much more clear. So this is carboxylic acid. Carboxylic acid. And then we have another class here now. This class is when the terminal carbon of the carbonyl carbon is in the first carbon, usually at the terminal carbon. That means here it has to have a hydrogen to saturate this carbon. This functional class is the aldehyde. Aldehyde. Or we also call them the alkanes according to the IUPAC. So these are common, and we cannot, like I said, it can also be double. When you have carbon to carbon double bond, of course, these are the alkenes. I told you, if you have carbon to carbon triple bond, this will be alkyne. So it must have either be the bond or the atom that actually places that particular compound in that particular group or class. And those particular groups or atoms is what we call the functional groups. All right, so let's look at the different classes of functional group and how they are used to actually do what? To actually differentiate different organic compounds into different classes. So we're going to have a quick look at all of them. I advise you to have this table. I have this table both in the worksheet as well, to keep this in mind until you begin to understand and identify these functional groups yourself in practice. So the alkanes, like I said, have carbon to carbon single bond. So like, it's fine if you always tell me carbon to carbon single bond, that is fine. And a good example here is what? Is the ethane. Ethane is the second member in the group of alkanes. So the alkanes, like I said, have carbon to carbon double bond. The double bond is what identifies them and places them in this class. A good example is the ethene gas. Ethene gas is the example in this class. The alkanes have carbon to carbon triple bond. You look at the triple bond here. This is what places them in this class. A good example is the ethane gas here at this point. The aromatic is characterized by the presence of the cyclic ring that have 3 double bonds around it. Alternating double bond. Alternating means there's a double bond here, but it jumps this carbon and comes to the next one. So this particular carbon is what we call the aromatic ring. And this aromatic ring is the simplest member is the benzene ring. When it has all the hydrogens here, is the benzene ring. Then that is so we call them the aromatic or the arenes. They can be called the arenes. Now the next group of compound is the alcohol. I already talked about this. The alcohol is known by this functional group. And a good example here is the ethanol. Ethanol is also called methyl alcohol. It's called methyl alcohol. Now, another group of compound we're going to be talking about, okay, this is called methyl, no, not methyl, ethyl, sorry. Did I ever say methyl? This is ethyl alcohol. Yeah, that's another name, the old name of this. Although most of our attention will be focused on using the IUPAC nomenclature to name them. The ethers are known by having oxygen in the middle between 2 carbons. This is usually the ether group. And a good example here is the dimethyl ether, usually the simplest of all that class. The aldehyde, like I had in the previous slide, the aldehyde have carbon, the carbonyl carbon to be at the terminal end. It's always at the terminal. Here, this is the carbonyl carbon with a hydrogen. Anytime there's a hydrogen here, they are the aldehydes or the alkanals. And a good example here is the ethanol or acetaldehyde. And then the ketones. Now, remember, the aldehyde and ketones are similar. The difference is that in the ketones, the carbonyl carbon is in between 2 carbons. So it can never be at the terminal. At the terminal, it becomes this. At the end, in between 2 carbons, it becomes ketones. A good example here is propanol or acetone, a very common ingredient that we use in the lab for a very good solvent for most organic molecules as well. And it's polar because of this. It has smaller molecular weight, and because of this carbonic carbon that is a polar functional group. Now, other ones include the carboxylic acid. The carboxylic acid had the carbonyl carbon and an OH group attached to the same carbon. So a good example here is the ethanoic acid or the acetic acid. We have the esters. The ester or the alkanoids. The esters or the alkanoids have the carbonyl carbon and something that looks like an ether bond again between 2 carbons. So it has this and this. So this is what we call what? The esters. The ester or the alkanoid. A good example here is methyl ethanoate or methyl acetate. So this is a good example. The amines have nitrogen as their functional group. Now this nitrogen can be attached to another carbon. This one can be attached to another carbon. But just anytime you see just only a nitrogen, that functional group is the amines. A good example here is the methenamine or the methylamine. The amides are just close to these guys. The difference between this and this is that this one has this carbon attached here to the what? A carbonyl carbon. That's the difference between these. So if you put all this together, you now form the amide group, both the amine and the carbonyl carbon. So a good example here is the ethanamide or the acetamide. So this is a very good example of this class. And the last but not the least is the thiols. The thiols are known to contain just sulfur-containing organic compound. So in this case, the sulfur can be in between two carbons, or it can also just be a hydrogen at the terminal. It can both in the middle or in the terminal. They are the thiols. A good example here is the simplest of them is the methane thiol. So these are all the classes of functional group that we're going to be studying in this class. That is important. You begin to practice on how to recognize them, and that will inform the first reflection question we're going to do. The question says, identify, circle. You have to look at it, identify it. You have to circle it, and you have to name all the functional group in this molecule. And in fact, this is usually one of the first questions you see in the midterm exam. So you must have to place more attention to recognize this carbon. So let's look at it. I'm going to start from here. If you look at COOH, first of all, we know this is what? Carboxylic acid. This is the carboxylic acid. And I'm going to say this is number 1. I'm just going to say number 1. Okay, if I finish numbering, I can number later. Let me just finish writing all of them. Now, I'm going to go to the next one. The next thing attached here, look at this. This is a benzene ring, and I told you the benzene ring is the aromatic ring, of course. So this is the aromatic functional group. This is the aromatic functional group. Aromatic. Or we call them the arene functional group. That is what they are, because the benzene ring, this alternating double bond, 3 of them, you find them in this ring. Now we go to the next one. I'm going to go to the next one. Look at this. This is C to O. Whenever you see a CO bond in between 2 carbons, remember what I told you? It becomes what? The ketones. This is the ketone functional group. When you have only nitrogen attached to hydrogen, or just only nitrogen, not attached to a carbonyl carbon, of course, this is going to be our what? This will become the amine. This is the amine functional group. Now, remember what I told you when I talked about carbon to carbon triple bond? You see, even in the review, anytime you have a carbon to carbon triple bond, the next bond close to it is going to be linear. See how linear this has become? Of course, the carbon to carbon triple bond, we know it to be what? What functional class is going to be the alkanes. Alkanes functional group. And then, close to that, we have another familiar one. If we just double bond in between them, it's going to, if it's just a double bond, it's going to be the alkenes. The alkane functional group. Alkene. And then we now go from there. We saw something interesting. This is when you have 2 carbons in between an oxygen, you have what? The ether functional group. And again, if you look at the ether, we have sulfur here, of course. Whenever you have sulfur, you have what? The thiol or the thiol functional group. We're moving on. Moving on, we see something here, OH, of course. Anytime you see the OH, this is what? The alcohol functional group. And then, look at this. I told you, when you see a carbonyl carbon at the terminal end, you see this is a terminal here. At the ending or beginning, whichever you want to say. You see, it must have a hydrogen to satisfy the octet rule of this carbon. In this type of thing, when you have a carbonyl carbon at the end, particularly, there must be an hydrogen to it. This is what? The aldehyde or the alkanes. Aldehydes. No, I didn't like it. Aldehyde. Aldehyde functional group. And then the next one, I think this is going to be the last but not the least. We don't see anything here. This becomes an amino group attached to a carbonyl carbon is what? The amide functional group. And some students may want to even give me carbon to carbon double bond. If you do that, if you give me carbon to carbon double bond as alkanes, I'm going to grade it. That is fine. That is okay. Quite okay for me in this class. So let me now label and see how many functional groups we've identified in this compound. So this is number 1. I'll call this number 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8. This is 9. Okay, I'll call this again 10. This is 11. And this is 12 functional group is what we'll find in this my hypothetical giant molecule. And it's important you know how to do this. And you're going to see this, like I said again, you're going to see this for sure in the midterm exam. All right, we'll now go to the next slide. Now we'll start talking about the classes of organic compounds. That's what we're going to now. Hydrocarbons. You see, hydrocarbons are compounds that contain only carbon and hydrogen, just as the name implies. Carbon and hydrogen, that's what it means. Now, hydrocarbons find ubiquitous use in our everyday life. They are used as a primary source of energy and is an important source of raw materials for the manufacture of plastics, synthetic fibers, drugs, and other compounds that we use daily in the household. Of course, if you talk about propane, that's what everybody uses this summer season. I'm recording this in the summer. You know, that is a source of energy to grill your steak. So they are classified. Now, hydrocarbons are divided into 4 classes. Now, but they have a broader class. The broader class is one, they can be saturated or unsaturated. The only member of the saturated class are the alkanes, where they are, because they have carbon-to-carbon single bond. You see, carbon-to-carbon single bond. They are completely saturated with hydrogen. Now, the unsaturated ones have 3 classes: the alkenes, the alkynes, and the aromatics. The alkenes have carbon-to-carbon double bond. We already saw this in the functional groups. The alkynes have carbon-to-carbon triple bond, while the aromatic have at least a benzene ring in it. They must have a benzene ring in their structure. So these are the 3 or the 4 classes of hydrocarbons we're going to be talking about. So what then? We're going to start with the first one, the alkanes. So alkanes are the simplest group of organic compounds. Of course, like I told you, they have carbon-to-carbon single bond as their functional group. Or you just said they don't have functional group. That's okay. Now, they have a general formula of CnH2n plus 2. Particularly the normal ones. We call it the normal alkanes. The normal alkanes means they don't have any branching and they are not cyclic. Well, I'm going to show you what that means. Now, where N here represents the number of carbon atom in the molecule. So you can easily say, so if you have C1, for the first one, is 1 carbon. If you have C1, it's going to be C1, H2 times 1 plus 2. What this gives you, C, you don't have to show, anytime there is 1, you don't have to show. This is going to give you C, H, 2 times 1 is 2 plus 2, 4. So this is the simplest member. And this is what we have here, the methane. Of course, this is the ball and stick model. Remember, this is the ball, no, sorry, this is the space filling model. This is the space filling model. I showed you this thing earlier. Space filling. This is the space filling model that shows you the relative sizes of each atom. Now, both in the space filling model and the ball and stick, these are all ball and stick. This one is the ball and stick. This is ball and stick. This is also another ball and stick. Now, in the ball and stick, both in the ball and stick model and this, now look at what happens. You see, carbon is usually represented by black or gray, depending on the software. Black or gray. So this is carbon. This hydrogen is usually white. Hydrogen is always white. So this is carbon, carbon, hydrogen, 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 hydrogen. You're going to do this in the first lab. So it's important you start getting used to them at this material time. Now, so the simplest member is the methane gas. Of course, the methane is used as a source of fuel, both industrially and like in my country, our common domestic gas is methane, not propane. That's what we use, even in some household in some other countries as well. All right, so methane is the simplest alkane and is a primary source of natural gas, of course. Ethane is the second one. This is the second compound, C2. Ethane is C2H6. If you apply that formula again, I'm not going to do that. You can do that on your own. Now, is a minor component of natural gas as well. Propane, of course, on the other hand, propane is the most important. This is the one we use in our grills. It's used as industrial fuel and for heating in homes and cooking. If you want to do your steak, this is what you're going to use. And these are the common ones we're going to be seeing. So now I can undergo isomerism. Remember we said earlier, when I introduced isomerism in the first lecture, is it the first or second lecture? Okay, which any of them. Now we said isomerism is the existence of what? Organic compound with the same formula, but different structural arrangement or arrangement in space, geometric arrangement, right? Now we start talking about structural isomerism. So we'll continue talking about that now. The structural now, so alkanes undergo isomerism. So isomers of alkanes can either be normal or branched. Normal means it has a continuous chain. Branch means one of the carbon is an attachment. Let's see what happens. So in a normal alkane, all the carbon form a continuous chain. This is a normal alkane. Now, if I'm going to satisfy this, remember they are saturated with hydrogen. This is a normal alkane, of course. This is butane. It's a good example. 1, 2, 3. No, this is 1, 2, 3, 4, 5. Oh, this, my bad. So this is not butane. This is a mistake here. This is 1, 2, 3, 4, 5. This is pentane. And pentane is C5H. 2 times 5 plus 2 is going to give you 12. That's what. So this is pentane. Please make sure you make that correction. 1, 2, 3, 4, 5. So this is pentane. This is the normal pentane. That's what we have here. A normal pentane here. In normal pentane, it has no attachment. All the carbon forms a continuous chain. Now, in the branched alkane, one of the carbon, at least one of the carbon can form a branch. Look at this one now. Here now, this is, let's take this as the longest chain. So let's count 1, 2, 3, 4, 5. This is 1, 2, 3. If this is the longest chain, this is an attachment. 2 methyl group is an attachment. So let's saturate these ones now. So this is an attachment. So these 2 methyl groups are attached in carbon number 2. They can also be attached in different carbons. And in fact, since this is 1, 2, 3, 4, 5 carbons, you can also have something like this. So this is a branched alkane. You can also have something like this. 1, okay, I have a space here. So 1, 2, 3, 4. And then you have just one attachment to it. And then when you satisfy the saturation for this, make sure you do that. Yeah, if you satisfy the saturation for this, see what you get. So here now, you find out this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All these compounds have the same formula, C5H12, but they are different compounds. This is a different compound with a different name, with different properties. This is a different one. This is a different one. So alkanes undergo structural or constitutional isomerism. So again, just to show you, highlight what I'm talking about, the branch and the branched alkane. And so in a normal alkane, again, this is butane 1, 2, 3, 4. It is a normal butane. Look at it. It is a continuous chain again. Like I told you again, carbon is usually gray or black. Hydrogen is white. So if you count, then this is the structural formula. Now here again, you have 1, 2, 3. So what you do, just break out one of these here and use it to form a branch. You cannot put it in the beginning. Again, the branch cannot be at the beginning. It must have to be at the second one, in the middle. So that is how we have this as a branch. So these are 2 different compounds. And this is the ball and stick models of isomeric form. So this is normal butane. This is what? Isobutane. In fact, this is the normal butane. If I want to name this now, this is going to be 2-methyl-propane. Becomes a different compound altogether, like I said. This is a complete different compound. And in fact, if I want to do the skeletal model, this is 4. I'm going to say 1, 2, 3, 4. 1, 2, 3, 4. If I want to do this, look at what I'm going to do. I'm going to say 1, 2, 3. 1, 2, 3 first, and then I'm going to have an attachment at this point. So this one is this, whereas this one is this. So you always have to practice on how to break up those terminal points and put it at the middle to form different structural isomers of alkane. So now, conformations of alkane. Alkane can also exist in different conformations. Different arrangement of atoms in space is achieved by rotation. Now you see, but if you go to the lab, I just show my student how this rotates. Now, the alkanes the bonds in alkanes can actually freely rotate because it's a single bond, it's not a double bond. If it's a double bond, it's not going to rotate. It's going to rotate a little bit. But here, it has free rotation. And this rotation can make it to form different conformations. Now, see, different conformations of alkane does not represent different structural isomers. It's the same thing. Look at what happens here. Now, this is a continuous chain. If I'm going to draw this now, look at this, looks like L. This is so there's a carbon here, there's a carbon here, there's a carbon here, and there's a carbon here. This is a continuous chain. The same thing here. Look at this one now. This one, what you're doing is that this one looks like an L. There's a carbon here, there's a carbon here, there's a carbon here. So there's no difference between these 2. They represent the same compound. So in each of these cases, the 4 carbon atoms are bonded in a continuous chain. Now, since the order of this bonding is not changed at all, the conformations correspond to the same molecule. It did not change. The bonding did not change. So if you put the hydrogens again, the formula is going to give you, this is 4 carbons. So this is still butane. It's going to give you the same thing. What only happened here is that, look at what happened there. You have rotated this. So now, you have it like this. When you move this one will move up. Look at what happened. This one will come here, and this hydrogen will go here. That is how you form this thing here. And this represents the same molecule. So this conformation are possible because of the free rotation about the what? Carbon to carbon single bond in alkane. They represent the same molecule. So we're going to use that to try to solve a few problems again. So now this is another good example here. So these are the conformations. This is another one. So this is a continuous chain. The same molecule, this is a continuous chain. Both of these are continuous chain. So if you put your hydrogens, okay, let me go back to my red. I usually like writing with red. Now, if you go back to this and put it, you find out that the number of hydrogen and the number of carbon is the same thing. There is no branching. It's just the same thing. The same thing here. Saturate this. Now, this molecule is the same thing. The difference, like I said before, here you have this, this, and this. And here you have this, this, and this. Represent the same molecule. There's no change. So this is what? The same molecule. The only difference is that the rotation made it to look in a different conformation. The normal alkane changed to different conformation, but they remain the same molecule, containing the same number of carbon and the same number of hydrogen. Now, let's take our second reflection. It says, which of the following pairs represent structural isomers and which of them represent the same compound? It says, which of them are normal alkanes and which of them are branched alkanes? Let's look at this. If you look at this, let's start from the A and B. If you look at this looks like a continuous chain, right? This is a continuous chain. What this is telling you is that, and let's count the carbon. This is 1, 2, 3, 4, 5. If I count this one, 1, 2, 3, 4, 5. This is a continuous carbon. What this tells us is that A and B are the same compound. They are the same compound. And are what? They are also normal alkanes. These are normal alkanes because they don't have any branches. Remember, there's no branching. These are normal alkanes. They are, like I said, they are the same compound and they're normal alkanes. Now let's look at C and D. If you look at C and D now, there's an attachment here. So this tells us that this is not a normal alkane because there's an attachment already. So let's count. If you always try to count and give the attachment the lowest number. So I'm going to give you the lowest number. 1, 2, 3, 4. So there's an attachment, a carbon number 2 of methyl group. Let me go back again and count this one. If you look at this one now, this one has changed conformation. You have to identify the longest chain. What is the longest chain? 1, 2, 3. It can be this one. 1, 2, 3, 4. This is the longest chain. If you count it from here, 1, 2, 3, you have attachment at carbon number 3. If you count from here, the attachment goes to carbon number 2. So I'm going to follow this counting. 1, 2, 3, 4. And then there's an attachment again in carbon number 2. Remember here, there's an attachment in carbon number 2 as well. And they have 4 carbon. The longest chain is 4. The longest chain is 4. Therefore, C and D are what? C and D are same molecule as well. They are same compound. Now, they are not normal alkanes. They are branched alkanes. They are what? They are branched because they have attachment. They are branched alkanes. That's what they are. Now, the question says which ones are normal, which ones are branched. We already said that. They say which ones are structural isomers. Let's see now. Let's see. You see, this is the same compound. They can be isomer. Since the formula of all this compound, if you write their formula, the formula for each of them is C5H12 because they have 5 carbon. Remember the formula: C5, 2 times 5 plus 2. 2 times 5 plus 2 will give you C5H12. All this compound will give you C5H12. That means this pair of these two will be structural isomer of this one. Look at this. This is going to be an isomer of this, right? This is going to be the isomer of this. This is going to be an isomer of this. This is an isomer of this. This is an isomer of this. So A stroke B and C stroke D are structural isomers of each other. They are structural isomers. They are structural isomers. Because all of them all have same formula. And what is the formula? The formula is C5H12. Yes, again, like I said, this is an isomer of this, and B is also an isomer of this. So what that thing simply means is that, again, this will be an isomer of this, and this is going to be an isomer of this, because this is the normal, this is what? The branched, and they have the same molecular formula. So that is how we do this problem. And then we get to the last problem, the last but not the least of all, is reflection number 3. In reflection number 3, almost a similar question again. It says, which of the following pairs are structural isomers? Which of these are simply different representations of the same molecule? That means they are conformations. When I say different representation, that means they are the same conformation. There are different conformations of the same molecule. Let's count. Let's see. Now, if you look at this, there's a branch here. Let's count. If I count from here, this is 1, 2, 3, 4. If I count from here, 1, 2, 3, 4. There's a branch point in carbon number 2. Let me count this one. There's a branch here. If you count 1, 2, 3, 4, it becomes number 3. If I count from here, 1, 2. So let's count 1, 2, 3, 4. So there's an attachment at this point. Okay, like I said, now, so this one has if I come from here, it becomes attachment to number 2. So I'm going to take this counting that gives the attachment the lowest number. What do you now see? These two compounds are the same thing, because the attachment is carbon number 2, and they have the longest chain to be 4. So I'm going to label, let me just label this with a different color. Let me say A. That didn't come out. A, B, C, and D. Yeah, let me just label it then. So what are we now going to say? So A and B are same molecule. They are the same molecule. A stroke B. Oh, I should have used A and B. What is going on? Are same molecule. Why are they same molecule? I can actually that reason in exam, because each of them have a continuous chain of 4 and an attachment in carbon number 2. So that makes them the same molecule. They have an attachment of branch at carbon number 2. So that makes them the same molecule. So let's look at these two, C and D. If you look at C and D, 1, 2, 3, 4. If you count this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I'll start counting from here. This 1, 2, 3, 3, 4, 5. So there's an attachment in carbon number 2 here. I count this one again. 1, 2, 3, 1, 2, 3. So I'm going to count from anywhere. It doesn't matter. 1, 2, 3, 4, 4, 5. Now, so let's look at, we've talked about the first pair, what they are and the reason why. The second pair, C and D. See, C and D are not the same molecule, because here the attachment is in carbon number 3. Here the attachment is in carbon number. So both of them are branched. So you can say C and D are both branched alkane. They are both branched alkane. Granted. But remember, this is also a branched alkane as well. They are the same molecule, but they are branched as well. I don't write. Let me write. They are branched as well, both of them. So we have both branches in both cases. They are both branched alkane. However, they are not the same molecule, right? They are not the same molecule. So they are different molecules. So you can say, okay, this is the first one. Remember, this is for the first question. This is for the first one. Second one, I'm talking about C and D now. So let me say this is, let me try to differentiate. Let me say A. So this is B. Now let me try to answer the question that way to make it clearer. Now, so C and D are both branch alkane, just like the A and B. However, they are different molecules. Remember that they're different. Why? They're different molecules because C has a branch point at carbon number 2, whereas D has a branch point at carbon number 3. So they are different molecules. However, what word will you use in identifying them? What can you say about them? They are isomers. So they are different molecules. Or you can say they are different molecules. Yeah, let me write that. They are different molecules. They are different molecules. And isomers of each other. They are isomers of each other. That's what they are. They are structural isomers. Particularly, they are, okay, let me put the word. This is the last I'm going to do, so it doesn't, let me use the correct word. They are structural, and they are structural isomers of each other. Like I said, the first one, they are not structural isomers, the same molecule. The A and B are the same molecule, they are not isomers. Whereas C and D are structural isomers of each other. Remember again, both of these are all of them are all branched alkanes. So you find out that this branching is actually what brings about this isomerism in alkanes. Thank you once again for listening at this point. We've come to the end of this lecture. Bye.